Hello everybody, this is Dr. Thunder. Today, I would like to show you how to solve a US high school physics competition question. So we have a wheel of radius r that has a thin ring and four spokes. Each of the four spokes has uniform density. The entire ring has a mass of m, and then three spokes have mass m each. And then the fourth spoke has mass 3m. The wheel is suspended on a horizontal frictionless axle passing through its center. Now, if the wheel is slightly rotated from its equilibrium position, for example, rotated that way, then what is the angular frequency of such small oscillations? So first, we want to show you a formula. The relation between the torque, moment of inertia, and angular acceleration, tau equal to I multiplied by alpha. So tau is the torque, I is the moment of inertia, alpha is the angular acceleration or second derivative of theta. Theta is the angle. Now first we want to know what is the moment of inertia. For example, take this spoke. It has a uniform density. It has a mass m. If you can memorize it, then that would be good. We know the answer if we take this as a pivot point, and then the moment of inertia for this spoke will be 1/3 mr squared. R is the length, m is the mass. But if you forgot the formula for the moment of inertia, we can do a quick integration. We can do a quick integral. So let's set up coordinate first. So this is O is the pivot point, and then this is x-axis, and then the length of this spoke is r. So we take any point x, and then we take a small section dx. So for dx, the moment of inertia will be di. That would be m, which is dm, and then the distance from pivot point to here is x, so it's x squared. So we know that dm, because the spoke is uniform in density, so dm equal to m over the whole length r, and then the length dx, and then multiplied by x squared. Now we integrate the whole thing. So I is integration of di. We integrate from 0 to r. So we plug this term here, then move the constant out. So then we get this. We'll plug r here, and then minus the term that where we plug 0 here. If we plug 0, it becomes 0. So the final answer is 1/3 mr squared. Now, the total moment of inertia, including these four spokes and then the ring outside, will be I is, this is for the ring, because the ring has a mass of m, and then the distance to the pivot point is r, so mr squared, and then we have four spokes, so first 3 is m, the last one is 3m. So eventually the total moment of inertia for the whole thing is 3 mr squared. We denote that as a formula equation 1. Now we want to find out the the torque. Torque is produced when we rotate the whole thing from its equilibrium position slightly. So we draw a line here. This line represents the new position. So assume it has an angle theta here. Remember, theta is very, very small. So we only rotate from its current equilibrium position by a very, very small angle theta. So for this spoke, its gravity is 3 mg, and then from here to here is R/2. So the component that pull this system back to its equilibrium position would be 3 mg. So the force here is 3 mg sine theta, and then the length from the pivot point to this force will be R/2. So this is the first term, 3 mg sine theta multiplied by R/2, because this force will return the system into the previous equilibrium position. So we put a minus sign here. And then same thing for this bar. And we know that it has a gravity of mg. Again, the component here is mg sine theta. And then the distance from the pivot point to this force again is R/2. So this is the mg sine theta R/2, but this one will keep sending the whole system away from the equilibrium, so the sign should be positive. Now we add these two terms up, so eventually we get this. Tau, or the torque, is minus mg sine theta r. Because theta is small, so sine theta is almost equal to theta. So this is formula 2, equation 2. Now, as we know from this formula, alpha, or the angular acceleration, or the second derivative of theta, is tau of I, or minus g theta over 3r. That's equation 3. Now, to solve this equation, we assume theta equal to a sine omega t plus b cosine omega t. And then first derivative looks like that. And do a second derivative, it looks like that. And then this one can be cleaned up to become minus omega squared theta. So that's equation 4. Now, if we look at equation 3 and equation 4, remember on left side is theta, second derivative of theta. So this term should be equal to that term, which means omega squared equal to g over 3r, or omega equal to square root of g over 3r. This is answer A. Or the angular frequency is square root of g over 3r. Thank you for viewing. If you like my video, please comment, like, and subscribe.